and I welcome you all to the third day of the workshop series of CIT Quantum Hackathon 2022. I'm sure that the past 2 days we all had a wonderful experience in getting into the world of quantum and Qiskit. With that same excitement, I'm elated to welcome Ms. Rohini as our guest speaker for the session. She's an IBM Qiskit certified associate developer, and she is so passionate about quantum computing and is the ambassador of Girls in Quantum India. She creates weekly posts about various quantum concepts and incorporates Tamil to those posts to make it reach more people. She has also participated in Qiskit localization program, and we are so thrilled to hear about the quantum entanglement, Rohini. And the stage is now yours.
Thank you, Dharmi. So now I'll start presenting and we can get into our topic.
Yeah.
So just a second.
We can see a screen, Rohini.
So yeah, so we'll get into it. So quantum entanglement, it's one of my favorite topics. It's a very special one too. So going on to the next slide. Um, yeah, this is the definition of quantum entanglement, a property in which a pair of particles is generated in such a way that the individual quantum states of each are indefinite until measured, and the act of measuring one determines the result of measuring the other, even when at a distance from each other. So this is just an definition, so you need not worry. I'll explain to you in the further slides. So now I'm going to tell you a story about two of my best friends. Okay, so one is Miss Sane and one is Miss Opposite. So the story one is about Miss Sane. So I'm here in India, and Miss Sane is in New York. So we are very close friends, and we are those twinning friends. Okay, like we are same in every action we do. So I go to a cafe and I order tea for myself. And as we are the same, she also goes to the hotel and she order without even ordering, she gets the tea. Like that's how close our friendship is. And now moving on to the second story, it is about my another friend. We all have that one friend, you know, who does the exact opposite things as we do, but still stays a best friend. So that is a Miss Opposite. And when I order tea here, he gets cold coffee there. So what you have to make sure about this in this slide is same, opposite, and the defined relationship. So when two objects are entangled, they share a defined relationship. That is, when you know one object states, you know the other as well. You know it can be the same, it can be the opposite, it can be anything. But with just one, you can determine the other. Like you can predict the other. That is known as entanglement. And entanglement occurs between two or more qubits. I hope this is clear. I'm moving on to the next slide. So this is some of the basics. Sorry, like this is the basic, and if you can put a little more concentration here, and it will be helpful in the further slides. So Q1 I marked red and Q0 I marked blue. So Q1, the first number in this is called a ket. So this whole thing is called a ket, and this is one more ket. Q1, the first number in each ket corresponds to Q1. So here Q1 is this red one, and this is Q1. The second number in each ket corresponds to Q0. Yes, simple, right? So I hope all of you got that. And moving on to the next slide. Okay, now I'll tell you about entanglement with some of the math involved. Okay, so just observe the state one here and make sure which is Q1 and which is Q0 as like in the previous slide. So concentrate here. So this is Q1 here. This is a ket. This is another ket. Now we'll deal only with state one, and then we'll move on to state two. So this is Q1 and this is Q0, Q1, Q0. Okay. Now, like they're given as some information. Now we make a measurement on Q0. Okay. Do you get it? We make a measurement on Q0 for this whole set. we make a measurement and we get zero. Like we put it into the quantum hardware and we make a measurement and we get zero as an output. So now the question is, but what about Q1? Just by making a measurement in Q0, does this tell anything about the measurement on Q1? Does this tell anything about Q1? Like, does this telling anything about Q1? No, right? Because we have 0 here, we have 0 here, and Q1 we also have 0 and 1 here. So Q1 is still in a superposition. It is not affected by the measurement on Q0. So I hope you got clarity in this one. And now moving on to state 2. Now you will get it more clear. And now it's the same, it's another state, and now the same thing. We are putting it in a quantum hardware and we are making a measurement and it gets collapsed. Actually, measurement, I like to say here that measurement collapses the states, okay? If it is in a superposition, measurement collapses to either 0 or 1, okay? That is known as measurement. It's according to the basis. If it is in the Z basis, the measurement collapses it to 0 or 1, and if it's in the X basis, it collapses to the plus or minus and accordingly. So for Q0, here we have 0 and here we have 1. So now we make a measurement, and due to measurement, it collapses to 0 state. Okay, that is the given information. So now does this measurement say anything about Q1? Obviously, as Q0 is in the 0 state, Q1 also has to be in the 0 state, because with the given information, as this is in the 0 state, Q1 also has to be in the 0 state. So yes, if Q0 is measured to be 0, then Q1 has to be 0. We are eliminating this state just by the measurement of Q0 as we get 0. Okay? So moving on. Okay, this is the summary of the last 2 slides. So entangled versus non-entangled. So what is the difference between entangled states versus non-entangled states? Entangled states cannot be factorized. That is, they cannot be written in the form of 2 separate qubits. Like if you see here, for state 1, this is not an entangled state. And this is an entangled state. So this is not an entangled state. So if you can, all of you know the factorization, right? We have done it in lower classes. The math involved in factorization, the FOIL rule, yeah. So if we can separate them, you can take Q0 alone, and we can write it as individual. We take common, right? We'll take common and we'll write and we'll multiply exactly the same thing. So now we are doing this here, and we will be able to, because Q0, both these states have 0, 0 and 1, 0. We have Q0 as common. So we are taking that out, and we can write it as common. But when you look at state 2, it can't be done, because these 2 kits don't have anything in common. So entangled states, they cannot be factorized, they cannot be written in the form of 2 separate qubits. And non-entangled states, they can be factorized and can be written in the form of 2 separate qubits. Okay, and the next differentiation is measuring on one qubit gives you information on the other. Yes, like when we measured this qubit, we got the information, and it did affect Q1 also. Measuring on one qubit affects the other. But here, these measurements are independent. Just we measured Q0 and we got 0, and then we have to again measure 0 and 1, and then we have to get the result. The Q0's result does not affect Q1's result. Okay. So measuring on one qubit gives you information on the other, and measuring on 2 qubits and the measurement on 2 qubits are independent for the non-entangled states. Okay, now we'll see the key concept alert. So all entangled states are multi-qubit superposition states. But all multi-qubit superposition states are not entangled. Only non-factorizable superposition states are entangled. Okay. Multi-qubit gates, in the sense, it can be anything with more qubits, like Q0, Q1, Q2. I'll show you the hands-on also. It can be anything, Q0, Q1, Q2, with a lot of gates, X gate, Z gate, and more. So superposition states occurs when we use a Hadamard gate. Okay. And entangled states occur when we use a Hadamard gate, and next the CX gate, the order matters, and I'll show you in a few upcoming slides. So that is the thing. So entangled states have to be superposition and multi-qubit, but it's not necessary for the vice versa. Okay. Moving on. Okay, why is quantum entanglement so special? Okay, because of exponential scaling of information. The exponential scaling of bits required to represent qubits only happens because of entanglement. Entanglement makes quantum advantage possible. Okay. With entanglement, we just need only 2 to power n classical bits to represent n qubits, and without entanglement, we need 2 into n classical bits to represent n qubits. Yes. Moving on. So, okay. Why did one of the greatest minds, Einstein, find quantum entanglement spook? Okay. Like one of the fundamental foundational insights of Einstein's theory of relativity is that speed of light is a fundamental speed limit in the universe. Okay, E is equal to mc square, like we all learned in our higher classes. So, like, what did that infer? Like, no, only with the speed limit is the fundamental, and the speed cannot we cannot exceed the speed. No information can be transmitted faster than that speed. Okay, but what does this entanglement say? Like you can be millions of miles apart, and if you affect one qubit, the other one changes too. And Einstein was like, oh no, how could that happen? My theory of relativity, it's violating my theory of relativity. So I was like, no, quantum entanglement, quantum mechanics must be incomplete. And he was against this. So what next? We have John Bell to the rescue. Okay, Einstein's argument was theoretical. It was he didn't give a chance for any experiment. He didn't experiment it just simply by the papers and by the theory. He concluded that quantum mechanics is incomplete, and he was like, "Oh no, this would violate my speed and etc." And he just concluded like that. But in 1960s, John Bell, the scientist who won against Einstein, who proved Einstein wrong. Like he showed an experiment to determine if quantum mechanics was right, or did it have any information that we have missed. So, what did the experiment say? The experiment is called the Bell test, and we've been doing this experiment proposed by Bell with increasing accuracy for over 40 years. In the 1960s, we didn't have much of the facilities and technology. By moving on to 1980s, 1990s, 2000s, and now we have increased technology, and we've done this. We are doing this experiment, and every experiment shows that quantum mechanics was right and Einstein was wrong. So I like to say here, this is one of the main reasons I love entanglement. It's like we've been studying Einstein's theory, Newton's theory, and we've just been applying it. But this is something which those great minds were at fault, and now we are proving them wrong and we are proving them right. So this is a field where you can create more things, invent, discover, and you can be an ex-scientist too. Learning is not just applying the formula and getting the answer. It's about validating things, and also it's about creating new and creating inventive things. And I think quantum is a field where you can be an ex-scientist too. So, and that's one of the main reasons I'm here. Okay, this is a very, very important slide. If you see, this must to create an entangled state. And this is what the order I meant. The Harman gate and next the CX gate. Like if you swap them, then that doesn't create an entangled state. So for every entangled state you create, there must be these two culprits. Like these two Harman gate and the CX gate is a must to create an entangled state. Okay, we talked about Bell, right, in the last slide, and he was an awesome person, and he created the 4 Bell states, and these are the Bell states. So, and this is the truth table of the Bell state, and this is a very, very important truth table, for the developer exam, for the advocate, or like you're doing some research in entanglement. This is a very, very important slide. So, like when you can just memorize it, like everyone memorizes it. So and we'll see the hands-on how to create these slides in a few minutes. So this is a very, very important slide. This is the truth table of the Bell states. Like if you put the input as 0 0, what output you get, as 0 1, what output you get, as 1 0, what output, and 1 1 as what output. That the truth table shows these. Okay. Next, we are getting into visualizations. What are we've seen this with truth table, right, of the Bell stage. So, like, how can they be visualized? So it can be in the circuit diagram, histogram representation, state vector representation, Q-sphere, unitary, block sphere, plot state city, plot state Hinton, and plot state polyvector. Okay. So why this slide is also important because for the developer exam, like you may get direct questions like what are the visualizations of available like for the well states, and they'll ask you, and that was a question for me also. So we are going to visualize these in all these forms. Okay. Okay. First, we'll visualize for the 0 0 state. For the 0 0 state, this is the circuit diagram, and it's a very simple. It's the base. It's called the basic bell state or the basic entangled state. Okay. So the input is 0 0 here, and then you create an Harman gate, and then you put a CX gate, and that's it. You get your first entangled state, and it's going to be 0 0 or 1 1. And this is the histogram, and we'll see all this in hands-on in a few minutes. And this is the state vector representation. Okay, and moving on. This is for the state 2. If you put the 0 1, if you it's for so what we're doing is here we are doing a 0 state. Here for the Q1 also we are giving a 0 state, and this we are leaving it as such because the input for Q0 is 0, and for Q1 it's going to be X and then H, and then if we create an bell state, a swap gate, and then we get a bell state 2. Okay, this is a visualization for third. So this is Q0 and Q1, and when you measure it, and we are putting X first here, and then when we are doing it, note here that for the Q-sphere representation, just because we have the minus sign, we are getting a different color. So Q-sphere shows us the phase differences too, and this is for the histogram. So this is for visualization of bell state 4. So for bell state 4, we are creating a 1 1. We are putting the input as 1 1 for both Q0 and Q1, and here also do note the phase change. Yeah. So we'll see. Don't worry with these slides. We'll see hands-on with these slides. So the next slide, like it's not we are not going to see hands-on, but like it's all just the visualizations. Okay, for 0 0, I'll explain plot state city and plot state Hinton. But plot state polyvector is like you have to memorize it or you have to note down. Like there's not more questions about. It's just a representation and a visualization, so you don't have to worry about. So for 0 0 and 1 1, you see the histogram stands at the four corners, same like for plot state Hinton. It's all different visualizations, so there's nothing much to explain here. And for the bell state 2, for 0 0, like you can see the markings here, like we mark our graph, right? The x-axis, the y-axis, the z-axis, exactly the same thing. So, and for this here, we have 0 1 and 1 0, and all the four histograms stand in the middle, the same as visualized in the plot state Hinton. Okay, awesome. And plot state polyvector, like all others are up and only the z basis is down. And for the first chain, all others are up and only the y is down. Like it doesn't have much of explanation. It's just a visualization. Okay. And for the third state, like this is somewhat interesting. Like for 0 0 and 1 1, we have the minus state as I showed you in the Q sphere. For plot state city, we have like two of them stand up and two of them stand down. And here you can note the color difference. See, here we have only white, but here we have black just for the, as we have the minus sign, the minus sign here denotes the phase change. Okay, and for this we have the XX down. Okay, for plot state Hinton. Moving on. Visualization of bell state flow. Okay. So for bell state flow, it's like 1 1 and the minus sign here. So we have it down, and we have it for 0 1 and 1 0, and yeah, all of them stand in the middle of 0 1 and 1 0, 0 1 and 1 0 with the color differences because of the phase change. And for this, the I stands up, and all others are down. Okay. So now I'd like to move on to the hands-on session. We'll have a notebook and uh, we'll get on like how to create the bell states, and we'll see some of the visualizations, and it would be awesome. Okay. Like you can now we are going to create the bell states. We are going to create an entangled states. That is, we are going to entangle two qubits, and we are going to see them in action. Okay. So for the first slide, let me run the first slide. Yeah. Now let us create the bell states. Yes, this is the first bell state. We have, so first I'm naming it as bell 0. You can name it whatever you like. You can name it your name or your friend's name or your best friend's name or anything you like. So bell 0, and it's quantum circuit 2 of 2, 2 comma 2, and 2 here represents the number of qubits, and 2 here represents the number of classical bits. So bell of 0 dot like this is the code for creating the first bell state. Dot h of 0, we want a h gate. What do we mean is we want a h gate in q0. And what do we mean dot for me a bell of 0 dot cx of 0 comma 1 is cx is it's a q qubit gate. So you have to give the target and you have to specify it. So 0 we replace cx in 0, and then we'll target it to 1, and I'm giving .ntl, which gives the circuit for us. So when you run it, yes, and you will get this one. Yes, yeah. So you'll get this one, and this is our first entangled bell state. So moving on. So now we are going to run it on a Qasem simulator, and what is a Qasem simulator? Qasem simulator is it mimics like a real quantum device. We are not running it on a real quantum device, but Qasem simulator mimics it to be a real quantum device. Okay, it gives us the result like if suppose we run it on a real quantum device, and we'll get a result, what would that be? So we have Qasem simulator for a rescue, and it will show us the result as like a real quantum device. So I'm going to plot it in a histogram, and you can observe it. Like we all know that it's the measurement is probabilistic, so we won't get 500 or 500, but we'll get really like about 500 to like. Okay, so this is 0 0 and 1 1, like we saw in the visualizations, right? So 0 0 1 1, and you can see like 0 0 has 512, and this has got 488. So if I run this again, it's for 1000 shots, and if I run it again, you will get a different measurement. But see, now we've got 504, 496, and it's going to be different, but it would be somewhere near to that 500. Okay, as the shots is given 1000. When you add this up, you'll get 1, like as it is in decimals, and it runs for us 1000 times and shows us the result. It mimics like an real quantum device. So this is that. So moving on, we are going to create bell state 2. So as I got bell 0 there, now I'm naming it as bell 1. So the same thing. First we are creating an H, H for Q0 and X for Q1, and then we are CX for from 0 to 1. And then when we run it, yes, we get this. Awesome. So when we get this, like this is the second entangled state. Okay. And now I'm going to run it to you in the histogram. So when you run here, so yes, now you'll get 0 1 and 1 0 with the same thing. Okay, with the same 1000 terms. 0 1 and 1 0. For the above thing, you noticed 0 0 and 1 1, and now we are noticing 0 1 and 1 0. Okay. So next. So next is bell state 3, and as I got bell 0, bell 1, we have bell 2 here. Like it's the same thing. It's the these are all the codes, and these codes are very very important. Like they can ask you how to create a bell state. Like you have to know these codes for creating a bell state, and this isn't the only code to create a bell state. You can like create in a number of ways. You can create in many number of ways for creating a bell state, but the only condition is you should have the hex and CX for creating a bell state. Okay, and the order matters. Hex and next only CX. Like if you swap it, you won't get a entangled state. Okay. Why is that so is because the hex states creates a superposition. Okay, the superposition, so it's like a 0 or 1, but if you put the cx before and then hex, it's of no use, right? Okay, so the hex state creates a superposition of between 0 and 1, and the cx gets makes the target and attacks the target, so we get it. So moving on, so we are in bell state 3, and this is the code. We are creating x for qubit 0, h for qubit 0, and then we are targeting cx from 0 to 1, and then you run it, and then you will draw MPL. Actually, MPL gives you the circuit output. Okay, with those colors, like gives you the circuit as such, so it will be easy for you to visualize. Yes. So this is the circuit, and X and H are here, and CX is there. Okay. And now, like now also, I'll run it for you in the histogram. When you run it for the histogram, you get 0011 with the probability. Oh my god, this is really really close. 499 and 501. We could have got 500 on 500, but that was really close. So moving on. So okay, 00 and 11. Now moving on to the bell state 4, known as bell state 3 here, because we've got 0, 1, 2, 3. Okay, and now. Let's create it again. Quant circuit 2 of 2 for the first we have x of 0, then x of 1, qubit for qubit 0 we have hex, and then from cx. Okay, so we get it to be visualized like this. Okay, and awesome. So now I'll run it for you in the histogram. When running in the histogram, like you get 0110 with the counts. Okay, like if you observe closely, like the representation of histogram, it shows 0110 here, and 0110 here. But these are two different bell states, right? For this is bell state 1, and this is going to be bell state 3, and how would you differentiate it with only the representation of histogram? The histogram doesn't show us the difference between the 01 and 10. It doesn't show us the phase difference. As I told you before, you'll get a minus sign in those things, and that minus sign indicates a phase change. But how does our histogram show? Pity of him. Don't worry, we have Q sphere to the rescue. Like Q sphere is another way of representation. It represents entanglement in a very very smart way. Okay, so this is Q sphere representation, and we are again going to run for the 4 codes, 4 bell states. Okay, and now this is the state vector, like I'd like to say, the state vector result of the bell state 1. Okay, and then this is the code for plot state Q sphere opposite, and then if you run it, our hero is here. We have the Q sphere result. Okay, so here you can see the phase. We'll see it within a few minutes or seconds or so. So for 0011, for the first bell state, if you have observed, we don't have any phase change. So it does shows us like this. Okay. Now going for the second bell state. So for the second bell state, as we have seen above, this is the circuit, and now I'm going to give you the state vector result. And You've got the state vector result also, and the state vector result is also a very important one. You can note it down, you can learn it very simple, and it would be of great use for you for the exams or for some calculations or so. And now we're going to get the plot state Q sphere result. The plot state Q sphere, like yes. So in the plot state sphere, Q sphere, for the Q sphere, we have 0, 0 here, 1, 1 here, 0, 1 here, and 1, 0 here. So for the second state, it's obviously like for the second state also doesn't have it doesn't have any phase changes. So we are gonna measure it's easy for us to observe here, right? Okay, and now like the real use of Q sphere is here. Okay, now we are gonna create well state 2. That is 0, 1, 2. We mean the third well state, yes. And we are going to run it, and you've you've got the circuit, and now one will run the state vector. When while running state vector, yeah, yes. Yeah, here you can observe closely that there is a minus sign here, like where I point the cursor. There is a minus sign here, and we've got our phase change. The minus sign represents the phase change. Okay. So now we are going to visualize this one. Okay. So now can you see the change in color? One is in blue and the other one is in yellow. So just because we've got the phase change, we are able to differentiate it here. Like for the first thing, you will be able to see like it doesn't show any phase change, and for this we've got phase change. Yes. Okay. And now for Bell State 4. Yes, I have run the code, and you have seen this above, and then here. So got it to be this one. Yes, we have got the state vector result, and now if you can observe closely, you can find the minus state here. Yes. So now we are going to get the Q-sphere result. Okay, and you observe here, like we've got the 0, 1 to be yellow and 1, 0 to be blue, because for 0, 1 we have a phase change, we have a negative sign. So you can compare this with the second Bell state. So I'll take you there and see there's no phase difference here, but you can see phase difference here. Yes. Okay. Next, moving on to something more mathematical and something very important for the exams and for the calculations and so. So that is unitary representation. Unitary representation. So, so yeah. So again, we create the Bell states. So we created the Bell state, and the result of the unitary representation is very important. You will need it for more and more calculations, and if possible, you can like by have them. They'll ask you directly like what was the representation. Yes, yes, and this is the unitary representation of first Bell state. Yes. So moving on for our second Bell state. Like yes, we've got the circuit, and this is the unitary representation for our second Bell state. These are the codes. Like do pay attention for all of the codes, because there are a lot of watching. There are a lot of questions about it, and you'll get the codes as like fill in the blanks or match them, or which is correct, which is wrong. Like you get them as such. So yeah, so this is for the third bell state, and this is the unitary representation of the third bell state. Okay, and here comes a fourth bell state. This one's the circuit, and this is the code for the unitary representation, and we've got yes. So this is more mathematical, but it's really really useful. And while taking the examinations, I had to pay a lot of concentration to this one because, like there were quite a few questions regarding this one. I'm meaning this for the IBM Biscuit Set examination. If anyone of you is taking up the exam, like it's a very useful one. And to become a Quiz Kit advocate, also this exam is a pathway. Yes. Now we'll go move on to block sphere representation. Like block sphere, like if anyone's when I was new into quantum, and I was very very fascinated about block sphere representation. It's a 3D sphere. It represents anything very very clearly, and you can see a lot of mistakes. But to my surprise, like I'll show you how it represents the entanglement. Okay. To my surprise, this block sphere, what did it do was, yes, it did show me only this. Yeah, you can never understand. This how this block sphere represents anything and everything very beautifully and clearly, but at last when it came for entanglement, the Q sphere, but we have Q sphere to the rescue, and Q sphere represents it very very carefully. Like there may be questions for you asking how does a block sphere represent an entanglement, and this is the answer. It doesn't show you anything regarding like where is it, when is it, like while studying entanglement for the first time, I was like this. I was confused. Oh no, how could that change be? How could one measurement on Q0 be affected by Q1? And I think the block sphere got stuck there. It got affected, and it doesn't show you anything. But don't worry, block sphere is a 3D representation, whereas Q sphere is a 2D representation. And this one represents entanglement wonderfully. Yes, at times more than 3D, 2D is well like old school. Okay. Now I'm moving on to the slides. Like okay, like we've learned the entanglement so far, and we've been amazed by this awesome property of quantum mechanics. So where are we using it in real life? Okay, application. It is superdense code. Okay, superdense coding is about efficient information transfer. Okay, what is oh, fine, Rohini, what are you telling about? Okay, so like you're gonna ask me why is this important, and why should we learn this one? And okay, so I've got an answer for you. Okay, in the year 2020, the average rate at which data was generated in the world was 600 Gbps. Okay, 600 Gbps, and the global average internet speed was approximately 30 Mbps. So, which is almost 20,000 times slower. It's 600 Gbps and it's 30 Mbps. So, it is 20,000 times slower. So, like, you've got the data, you've known how to process it, you have the other end people who can take the data and they can make wonders about it, but it's like you don't have the correct internet speed. So this thing would be a very big backlog for us in the future, right? For us in the future. So like and in the upcoming years, like by researchers say that by 2025 we are gonna generate 40,000 Gbps of data, like 40,000 literally, 40,000 Gbps of, see how huge it's just 600 Gbps and we've got only 30 Mbps, and by 2025 we are gonna generate 40,000 Gbps. So, but this speed is going to be slower. It's going to be slower. So, in the upcoming years, we're going to generate more and more data, and it becomes increasingly difficult for information transfer speeds to keep up. Okay, like this one is going to be a major issue. Like, so why are you saying this now? Like, what is the use? Okay, like we have next slide for us. So, entanglement attacks. Don't worry, we have entanglement for us to save us here. In superdense coding, we can use entanglement to communicate the same information by sending half many as qubits as classical bits. That is, like what I am meaning to say here is, by sending one qubit, we will transfer 2 bits of information. One qubit is equal to 2 classical bits. So, by using the same technique, we could half the required speed for information transfer. With just having half the speed, we can double the information transfer. Okay, I'm not going depth for super dense coding. Like, it's one of an awesome application. So, of entanglement, and it's going to be uh, implemented in a few years, I hope so. And so what we have to note here is the H and the CX gate. Okay, the thing we just created now, many times I did create it many times. So we created just back in the hands-on is the major part in the superdense code. Okay, so like in a nutshell, I'd like to cover what all I've said here. So objects which are entangled share a defined relationship. I told you the story, right? Miss same, miss opposite, and the distance between them and me. And like the tea or cold coffee you're gonna order, it's going to be the thing. And the measurement on one qubit affects the other qubit. Like on the we saw it with a mathematical example, like when we measured Q0 for the entangled state, it did affect Q1s. Okay, and entangled states cannot be factorized. So we cannot factorize entangled states, and those states which cannot be factorized can only be entangled states. Okay, for entangled states, we have to have multi-qubit superposition, and with the states which cannot be factorized. These are the rules for to make an entangled state. And exponential scaling on information, we need 2 power n classical bits to represent n qubits. Okay, and then we have the bell states, the 4 bell states, very important thing. And we have visualizations. We've seen a lot of visualizations in today's session. Like one of my favorite is QSphere. You know, it beautifully shows how to. And the thing I fear is unitary, because I tend to forget it a lot more times. And but you do have to pay concentration for the unitary, because that's the thing where many questions for the exam, we get many questions from the exam for the examination. And the QSPR is a very easy thing to remember. And then we have application superdense coding. So these are the references, and you can go through them. And then for any queries, you can contact me here, and just my mail ID, this is my LinkedIn ID. So yeah, thank you. Like if anyone has any doubts, you can ask me.
Hello.
Yes.
Yeah, madam. I am very new to this area. Just I have one very basic question. Uh,
Okay.
yeah, when you say entangled between the two qubits or two atoms, right? Or if they are very far apart, right? How they are
Yeah.
meant in reality? Is there
So
any communication between the two atoms or the two qubits?
we entangle them. You take qubit one here, you take qubit two here, and yeah, we created the bell states, right? You
Correct.
saw them.
Yes.
Yeah, we do some creation for them. You entangle them and then you throw away them. You can throw it any far. You can throw it to photons. You can throw it to the next universe. You can throw it to the next galaxy, and you throw this one also. And when this one spins, this one also spins, and it can be in the same spin or in the opposite spin, and that's entanglement.
Okay.
Okay. Hope I cleared your doubt.
Yeah.
Anyone else? So I'm a high school student, and I've been into quantum computing just a year back. So this is how I learned quantum, and I think so. This was my understanding of quantum computing. I take it into real life applications, and this is how they taught me too. So I'm not going to go more mathematical. Like if you see the Bell's theory and Bell's test theory, and if you go into Einstein's theory and all, it's a lot more complicated. It's not as easy as I say. There's more complications, but for us to understand, I think this is a very easy way. And I want all of you to remember that if I can do it, you guys can also definitely do it. Like I have, I'm a like Sir said, I'm also a very new student here, and you just have to spend some time for quantum, and you have a lot more resources, you have a lot more persons to help you. And this hackathon, for example, we can bring them together, and it will help you a lot. Like you just have to spend some time, and you'll understand things at a greater ease. Yes.
So there is no doubt from the participants.
Thank you.
And I should say it was a wonderful presentation, Rohini, and
Thank
the
you.
session
Thank you.
was exceedingly informative. You
Mhm.
made it very clear about the quantum states and working in the IBM quantum lab,
Okay.
etc.
Glad to hear that.
Thank you for joining us in sharing your knowledge.
Yeah.
And I, behalf of my team, wish you all the best for your future endeavors.
Thank you, and I thank everyone here for giving me the opportunity. And I thank CIT Quantum Hackathon Fall Fest, and I thank Dr. Mansula Gandhi, and I thank all the volunteers here. Yeah, you guys are rocking, and you guys keep going.
Thank you so much.